Welcome. Today we're going to talk about torque. Torque can be thought of as a rotational force. Recall Newton's first law. An object in motion will stay in motion unless acted upon by a net force, and an object at rest will stay at rest unless acted upon by a net force. Here's the rotational version of Newton's first law. An object that is spinning will remain spinning unless acted upon by a net torque, and an object that is not spinning will remain not spinning unless acted upon by a net torque. We use the Greek letter tau to represent torque. And the formula for torque is torque equals Fr sine theta. Take a look at this picture of a girl doing push-ups. She's rotating about her feet. In order to cause that rotation, she's applying a force with her arms. Notice this blue line. This blue line is called the angle arm. This is R in our torque formula. It's how far you are from the place where you apply the force to the place where you're rotating about. Notice also that she's applying the force at a right angle to the angle arm. Since the right angle is 90 degrees and the sine of 90 degrees is 1, pushing at an angle of 90 degrees will maximize your torque. So a torque is how hard you push multiplied by how far away your force is from the rotation multiplied by the sine of the angle of your push. Here we have it in plain English. F is force, R is the angle arm, or the distance from the applied force to the axis of rotation, and theta is the angle the force makes to the angle arm. Even dogs are familiar with torque. I bet you've never wondered why on your refrigerator they put the handle on the side of the door opposite the hinges. That gives us the greatest angle arm, and that maximizes our torque. So the dog is pulling this refrigerator door open from the handle. The axis of rotation is going to be on this side where the hinges are, and he's pulling roughly at a 90-degree angle to the angle arm. Rotational inertia is an object's resistance to angular acceleration. It depends on an object's mass and how that mass is distributed. Notice this athlete in the hammer throw competition. He's swinging this heavy ball around the axis of rotation, his body. Because all the mass is concentrated at the full radius, the formula for rotational inertia in this case, I equals mr squared. In the case of this car wheel, all the mass is going to rotate about the axis. But notice that not all the mass is out at the radius, at the full radius. Some of the mass is out here, some of the mass is in the middle, some of the mass is really close to the axis. So the rotational inertia of an extended object rotating about its own axis is a bit more complicated. Fortunately, there's a nice list of the moment of inertia, or the rotational inertia of extended objects. Wikipedia has a nice list. So if we take a look, here's our rock swinging on a string. All the mass is out at the radius, and the rotational inertia is mr squared. Take a look at the solid rod rotating about the center. The moment of inertia of this rod would be 1/12 ml squared. You're going to notice that there are always some fraction, well, not always, but almost always some fraction times mass times some distance squared. If we were to take the same rod and rotate it about the end, we'd find a different rotational inertia. That would be 1/3 ml squared. Here's a solid hoop. Again, it's mr squared because all the mass is out at a full radius. They put an approximate symbol here because there is a little bit of thickness to this that we didn't take into account. Right here is a solid cylinder. It gives you different axes of rotation, so we could rotate it about the z-axis, or we could spin it about the y-axis or the x-axis. Here's some important ones. A hollow sphere, for example the globe in the classroom, would be 2/3 mr squared. But if that globe happened to be solid, it would be 2/5 mr squared. Now let's talk about angular momentum. Recall our momentum formula. Momentum equals mass times velocity. We use capital letter L for angular momentum, and instead of using m for mass or inertia, we're going to use capital I, and instead of using v for speed, we're going to use lowercase omega. L equals I omega. That's our angular momentum formula. The important thing to know about angular momentum is that in a closed system, angular momentum is conserved. Let's take a look at the case of an ice skater spinning. When the ice skater's arms are outstretched, her rotational inertia is great as more of her mass is farther from the axis of rotation. But when she pulls her arms in, her rotational inertia gets less. If her rotational inertia gets less, her angular velocity must get more. Because I times omega is a conserved quantity, these two will always multiply to the same value L. If she can decrease her rotational inertia, her angular speed must increase as a result. Finally, let's talk about rotational kinetic energy. Earlier we learned that the formula for kinetic energy is K equals 1/2 mv squared. And you're going to find that the kinetic energy, the rotational kinetic energy, is K equals 1/2. Instead of m for mass, we're going to use rotational inertia, and instead of v, we're going to use omega, angular speed, squared. K equals 1/2 I omega squared. Recall that in a closed system, energy is conserved. Energy cannot be created or destroyed, but it can be transformed from one form to another. In the case of a ball rolling down a ramp, the ball is actually going to be going slower at the bottom of the ramp than if this were just some block on a frictionless ramp like we've talked about earlier. And that's because at the top of the ramp, when the ball is at rest, it's not spinning. At the bottom of the ramp, it's spinning, and it takes energy to make something spin. As an example, let's see if we can calculate how fast this ball is moving at the bottom of a ramp of height h. Let's pretend this ball is a billiard ball, so it's a solid sphere. Let's set this up as a conservation of energy problem. At the top of the ramp, the ball has potential energy, gravitational potential energy. It doesn't have any rotational kinetic energy or translational kinetic energy, as it's not moving or it's not spinning. But as it reaches the bottom of the ramp, the gravitational potential energy that it loses becomes kinetic energy and rotational kinetic energy. Okay. That is to say, mgh becomes 1/2 mv squared plus 1/2 I omega squared. And from our list, we see that a solid sphere has a rotational inertia of 2/5 mr squared. So I'm going to replace I with 2/5 fifths mr squared. Also, recall from earlier that our translational velocity equals r times our rotational velocity. We can rewrite this as omega equals v over r. So omega squared can be written as v squared over r squared. Our r squareds cancel out. This is important. We actually don't need to know the radius of the ball to figure out this problem. And every term has an m in it. We also don't need to know the mass of the ball. And 1/2 of 2/5 is simply 1/5. So all this is going to simplify into GH equals 1/2 v squared plus 1/5 v squared. We can add these together with the common denominator. GH equals 1/2, let's call that 5/10 v squared plus 2/10 v squared. And we get that GH equals 7/10 v squared. So a little bit of cross multiplying gives us 10GH over 7 equals v squared. And of course we don't want v squared, we want v. So we'll take the square root of both sides. And there's our answer. Okay. You now know enough to do all the assignments posted on your Raindrop page. Good luck. Email me if you have any